Oh, hello there. Yes, we're doing one of those things now. I guess what's going on? Memes. Oh, wait a second. This isn't breaking the multiverse. Hold on, I don't need this background here. Let's see the visual effects. Blah blah blah. Professional YouTuber. There we go. There we go. Ah, yes. All right. So after, oh God, how long have I been doing YouTube for? God, like 2018. So no, okay. In this instance, maybe like 8 years. Hold on, let me go to my YouTube channel. It says that there. Let's see. So this will be the first annual AMA. Why? Because I don't know. Am I gonna put together a full show on something and just kind of, well, that's what I usually do. It sounded appropriate because people a lot of times ask questions. A lot of times I ignore them. So let's actually get to the questions. First off, may Chuck Norris be at peace because apparently it's passed away earlier. It's sad. As somebody that look, I'm not gonna lie, I didn't really know who Chuck Norris was aside from, oh, that sounds like a celebrity, until I became a MC Raider. And when you're in the molten core, you just start hearing it's like, yes, behind Chuck Norris's beard rests a third fist. And all I know is in Death Battle they had Chuck Norris versus Sega Sagato. Long story short, they kind of destroyed the universe. So apparently, for somebody that has runs a show called Breaking the Multiverse with Fizz, it resonates. So condolences to his family. All right. So that is out of the way. First off, Rick, what does AMA mean here? It means ask me anything. Thank you, Poindexter. Yes, that is what it is. My favorite flavor of quark. Well, the top quark, of course. Why? It's the beefiest of them all. It's pushing like 172, 173 GeV. Why does it get so beefy? I don't know. We appear to have three generations of. I mean, for me, I'm just like, well, if we're gonna quantize stuff, it's like you're gonna have an energetic reaction. It's like, all right, I think the phone is gonna be most stable, as my friend Sebastian may say. Um, we may tend towards lower entropy in the formations. Now, entropy, at least according to the second law, tends to increase. Now, on aggregate, that might be the case, but within, okay, I'm going to use an incorrect analogy here. I kind of view it as like, all right, computational irreducibility. It's like, all right, when there's some entropy, we got to play it out, play it out, play it out. But there's going to be pockets of some form of reducibility. Now, you can make the argument, and again, I'm not a thermodynamist and stuff. Maybe ask Professor Wolfram about that. He's written some articles and believes he finally understands the second law of thermodynamics. Now, people can disagree. I don't know what's going on. I just something microstates. Thank you, Boltzmann and Jen, for bringing that to my attention, because that's where I mostly heard that from first. All right. Where are we? Where are we? Yes, welcome everybody. We got Poindexter and we got Thomas. Welcome, Thomas. Good to see you and everyone. All right. All right. Okay, so Rick is referring to the symbol. It's a little box symbol. It's in the 288 constants of nature. Let's see. Physics. Monastery. I swear I can spell. Thank you, autocorrect. Yes, you visit here often. All right, so let's share the page. No. I swear I know how to use this thing. All right. So that's basically the inversion boundary. To be fair, that's a good question. I don't even know if it has a formal name. It's literally just the inversion boundary. It was originally 10 to the minus 7, then went to the monastery. I'm doing the calculations. I'm like, all right, it's really close to 10 to the minus 7 using the numbers that he had derived for the claimed closed forms for the different Planck constants. But it wasn't 10 to the minus 7. It was like 0.99999919 99 times 10 to the minus 7. So it's really close. And to be fair, even with the, I think they had it originally defined. It was like the magnetic constant or something, uh, because it's technically Ampere's constant, stripping out the dimensions. Let's see. Hold on, symbol legend. Okay, so it's the hyperbolic inversion boundary. It's this little box. It just used to have the plus sign there. Now he's kind of using this, and Casey has brought up that I think within mathematics and stuff that is a used symbol, but that just kind of using it because it's kind of like the cone of your space-time diagram within a box. And the claim is that something interesting is going on here, maybe around that seventh significant digit, because again, the quote that is often misattributed to Lord Kelvin, which technically came from, I think, Michelson from the Michelson-Morley experiments, which isn't even an exact quote. It was paraphrased as the future in physics simply lies within the determination of the sixth decimal place of accuracy, aka we know physics, it's basically done, we just need to get increasing precision. Okay, now that may have actually panned out, except as we got more precision things started to get really wonky, and a lot of that wonkiness seems to happen around the seventh significant digit. Why? Mm. Also, there's that whole pesky uncertainty in the gravitational constant because, well, we've only got that down to about 5 significant digits, and that's when we're constructing our Planck units. We're usually using big G, h bar, and c, the speed of light. Okay, speed of light, we have the 9 significant digits. H bar is literally now defined at 10 significant digits. Okay. The problem with big G is if you got like half the significant digits, what are you gonna do? That's sorry. Oh, I was making sure I was still talking. Oh God. There we go. I just wanted to make sure it was actually broadcasting there. Yeah, so it's the hyperbolic inversion boundary. HIB. If anybody's got a good name for it, totally open, and I'm sure Thad would appreciate it because that's literally just the claim. And as we can see, it's can we minimize? Nah, it's not gonna do the little thing either way I want. Oh well. Okay. Oh God. All right. So basically, the whole thing is that box is equal to Planck length times the Planck mass divided by the Planck charge squared, and then we're literally just taking the units and inverting them to cancel them out. So we get a dimensionless number. Now you can say that is a reckless thing if you accept that maybe there is some significance, or again, this is something a lot of folks can argue with, and again, there's a lot of valid argument there. We're almost instantiating a preferred unit basis. Why, baby? That seems crazy. If we're willing to entertain that, some very interesting things that can be done. At least I would claim. Now, again, I'm very biased on that, but it is that calls it the hyperbolic inversion boundary there. And if basically if you just take all that Planck length, Planck mass, divide by Planck charge squared, Planck mass, Planck length, I'll divide by Planck charge squared. It's going to give us Ampere's constant. Okay, as we can see, it's estimating here 10 to the minus 7, aka it is Ampere's constant, which is also, what's this? Oh, it's 1 over 4 pi magnetic constants, because just do 1 over that, you're going to find, oh, look, 12.56, blah, blah, blah. Oh, look. Oh, it looks like 4 pi. Now, I realize I did that very fast. The only reason I'm able to do this is because I was confused as heck for a while. I made all these mistakes, but going through and making mistakes again, and then eventually getting things right and going through doing some calculations, it's almost like that thing that they told you in school to do practice problems might actually be useful. Now, again, I understand. I can go into modern chat or a lot of these agential things. I can ask it a question. You can set a Lagrangian, do all this calculations and stuff like that. You can do it really quickly in things that might take me an hour to set up in Mathematica. But it's kind of gaining that whole intuition, like what might actually happen. Or when you make a mistake, and also, let's face it, if everybody makes mistakes, if there's a really complex calculation, you're just trusting it. It's like, are you sure? Now, again, there are modern tools to help clarify this, such as well, actually, there's a Wolfram tool that we're technically supposed to send out for computation. Yeah, okay, that was a very long-winded answer, but let's continue. Where are we? All right. Very cool. Yeah, no. This is the other thing I've realized. It's if you're trying to do something and pay attention to something else, depending on how ingrained and natural that thing is, it's going to throw you off. Because like if I go out for a run, if I'm trying to listen to like a high level lecture where there's lots of stuff that I don't know, like if I'm listening to Stephen Wolfram and Jonathan Garrod go back and forth about high level topics, I've literally put those on and immediately fallen down. I'll go be running, I'll miss something, and I'll trip. If I put on a whole bunch of just random anime music, maybe not much, if any, lyrics that I even understand, but I'm used to, usually fine. So it's interesting that we seem to have a fixed amount of consciousness we can apply towards different tasks. So that is interesting. Oh, inversion boundary with Ampere's constant. Yes. All right. Well, the inversion boundary it's literally Ampere's constant minus the dimensions. So we'll just take this, divided by Ampere's constant, should get 1. Guess it's 1. So yeah, it's and again, even I was going through, I'm like, wait a second, now wasn't it 10 to the minus 7 by definition? But you look at it, I only know just because I checked this the other day. Magnetic constant code data. Let's see. No, this is the 4 pi version. Hold on. Magnetic constant. Okay. So that would mean Ampere's constant is also fine structure constant, h bar, elementary charge, speed of light. All right, so let's. I'm gonna move this out and just so I can have it in front of me. Give me a moment. Wolfram Alpha. So let's do this. Actually, I haven't done this calculation before. Fine structure constant, h bar divided by elementary charge squared times speed of light. Okay, and that gives us Ampere's constant. That is interesting. Oh, thank you. I did not know this relationship. I'm assuming since it's elementary charge, and then the fine structure constant is over there. It's doing. Let's duplicate this. Let's just take this out. Take this out. Is this going to be? Oh, okay. So this is. See, I know if I take the square root of this is going to be the Planck charge squared. I'm pretty sure. Let's, or if I take the square root of just alpha. Oh, let's just do that. Okay, then we take the square root of the whole thing, and this should be the Planck charge. No, I was wrong. It's wrong dimensions. Oh, what if I invert it? No, I'm off. Do I not take the square root of that? Oh, it's gonna, okay. Oh, okay, I just need to invert the first time. Okay, so okay, that makes, okay, duh. Because if we rewrote this whole dang thing, just elementary charge squared over the Planck charge gives you the fine structure constant. So if you're gonna do it the other way, then it's just gonna come out this. All right. Okay, so this gives us the Planck charge squared because it's times 10 to the minus 36. Planck charge is to the negative 18th power. There we go. All right. This is interesting. Fine structure constant. All right. So if we take the alpha of the elementary unit of action, we divide it by the elementary unit of charge times the speed of light. We got mass. Okay, because that's got mass. Mass, it's 2, speed of light is taking off 1 dimension of length there. Hold on, we got a board for this. All right, let's see. Just keep track. All right, so we've got, oh God, this is, I take a random paper towel to, there we go. There we go. All right. There we go. All right. A nice semi-clean board. Or a semi-coherent AMA, am I right? All right, so we got alpha H bar. Hold on, I need to write this out. Alpha H bar. Blah, blah, blah. Elementary charge squared. Let's see. All right. So this is dimensionless. This equals, all right, Planck units. It's Planck mass. It's Planck length squared. So L sub P squared. And that's 1 unit of time. So Planck time. Elementary charge is I can't do that. Oh, that's alpha. Oh, it's canceling out there. Okay. Ooh, okay. So that'd be Q sub P of electron. All right. So charge E. No, charge minus charge. Okay. So no. Elementary. I'm just going to do elementary because it's not specifying positive or negative. Squared, and then c is the speed of light. So all right, so c, we're going to divide out 1 unit of length, and this is we're going to divide out 1 unit of time. Okay, so the speed of light ends up canceling out that second dimension of length, because we're dividing by c. So the numerator c is length divided by time. So we cancel out 1 dimension of length, 1 dimension of time. And okay, and then with alpha, this makes this the Planck charge. Oh, cool. All right. Sorry, I wanted to do that myself. What, the guy's going to talk about working through problems and stuff. It's like, he sees this thing. Let's just skip it. Got to at least try, right? All right, where are we? All right, Ask another AI. Yeah, hey, that's the thing. Yeah, it seems to work. It's almost like a little bit of competition and a little bit of collaboration can actually help. All right, let's see. Where are we? Well, the brain runs on 20 watts. Oh God, that 20 watts. That's an interesting thing. Well, let's do that. Come back over here. All right. Let's try this. 20 watts. Okay. We got some dimensions here. It's electric power. It's like energy per unit of time, because energy would be mass times length squared divided by time squared, because it's got that little negative thingy there, but that's an extra thing there. Okay. Technically, it would be mass times the speed of light. All right. Divided by the speed of light. That's kind of interesting. That okay? Okay. Maybe I just did this wrong just because I'm. Wait a second. Okay. All right. I was getting worried. I'm like, wait a second. It seems to be at least the first three digits of the Newtonian gravitational constant. 20 watts. It's wrong power and everything. It's off by 3 orders of magnitude. But I'm like, silly coincidence. That's divided by c squared. Get the mass out. All right. So we end up getting, I think it was 16 kilograms per second. The typical use of those dimensions are dietary recommended intake, or a mass flow rate, extrusion rate, mass change rate, melt flow, linear drag coefficient. Wow. Guess it really depends on how you're looking at it. 30, maybe 30 watt. I don't know. It's 30 watts high power output. Why does this number look familiar? I'm sorry. I just too much numerology. Don't mind me. It kind of looks like an inverted speed of light. Oh, of course, because I changed the number to 30. First, the first like three digits of the speed of light are 2.9979. So it's close to 3. Of course, it looks like the inverted speed of light. Okay. See? These are the weird things that I didn't understand. And then after making so many mistakes, can slowly start to figure out what may or may not be happening. All right. Well, that is fun. All right. Well, I learned something new. Okay. Yeah. All from just coming here. Hold on. Let's go back to CoData. I don't think it's Ampere. That's the Ampere 90. So interestingly enough, the Ampere, and basically these are some of the constants that they set back in 1990 to try to make things easier based upon the precision at the time. As we can see, that's a 1 followed by 1, 2, 3, 4, 5, 6, 7. When we get over here, it seems to not be. Huh. Oh, this is for the Ampere itself, the definition that we use. Okay, now we're just using elementary charge times seconds. Okay. Because right now the Ampere is elementary charge divided by seconds. Okay. Wait a second. Wait. Hold on. This is. No, it's coulombs divided by seconds. I think we're taking that ratio. Okay, we do this, and then I think we multiply by. Oh God, we multiply by this number. Hold on. It's. I remember that we just multiply by what it is. Whatever the heck the answer to this is. All right. So we take that number and then we do, was it elementary charge? Divide by seconds. And then we divide by that number. So this should give us 1 ampere. There we go. Again, it just sounds like a whole bunch of mathematical BS, but it's like, it's just a relationship between stuff and things. And a lot of the times it's like we're just treating this as values of 1. So it's, you see things enough times, you kind of start to pick up on it. If you played a video game and you see patterns enough times, you start to pick up on it. It's essentially the same thing. It's pattern recognition. Okay, so that would mean, because it would just be coulombs divided by seconds. Coulombs divided by seconds would also be an ampere. There we go. All right. I did a whole project on it, so you would think I would at least be able to square away a couple of units. There's only so many of them, at least, that we work with on a regular basis. On Wolfram Alpha, God, I got like 10,000 different units. All right, where are we? Yeah, well, that's the interesting thing, Poindexter, because apparently when a living creature is no longer living, apparently there is a form of light that just stops being emitted. My normal thought is, well, if somebody unfortunately expires, it's like, well, I mean, less temperature, so you think that, but apparently this was different. Oh God, hold on. Light goes away after death. Okay, so at least according to the AI overview, take it for what it's worth. Living beings emit ultra-weak photon emissions, UP, a faint natural light caused by metabolic processes. A 2025 study found this bioluminescence drops significantly or vanishes upon death as cells stop creating energy. While not visible to the naked eye, this life glow is measurable, reflecting active biological cellular activities. And a key word you may hear is biophoton. So these are things, or it's like if you happen to see like when a sperm meets an egg, once it gets accepted and everything, apparently there's a bit of a flash of light there, and you're like, that's interesting. It's I can't say if there's any divine property or anything going on there, but it's one of those things that make you go, huh, that's interesting. So no judgment there. Just listen, I hear a lot of weird things. I spend far too much time on the internet. I can't make this up. It's the reality is too weird. Yeah, so it's hey, happy Friday, Tony. Good to see you, my friend. And we're just feel free to put your questions in the chat and everything, and I'll do my best just to try to answer. No guarantees. I'm not saying I have any answers to what's actually going on, but I can ramble on and, like a lame language model, fill in what sounds like it should probably go next. All right, let's see. Where are we? All right. Yeah, that does seem to be true. All matter does seem to emit photons constantly. Yeah, we also all have a frequency, as does everything in the universe. It seems to be perhaps a beautiful symphony of stuff and things. God. Rick is commenting Chuck Norris didn't die at 86. Chuck Norris, 86 to his age. Oh, God. Oh, I'm going to hell. Oh, that's the interesting. Full disclosure. I still remember, like, I think was it sophomore year in high school, we were doing biology class. It was pretty cool. And then we got to osmosis. The subject just seemed pretty dry to me. Not now, pun is included, but just that particular topic at that particular time, at least in my life, as it was being expressed, it just seemed boring. It's like water goes in, water goes out, it balances and stuff. I found it boring, and apparently it's why we exist. So don't listen to me when it comes to anything biology related, because I got no idea or any taste of what is or is actually going on. God, I saw one of those memes where what was it? It's you have the picture of the Grim Reaper, and it's like the Grim Reaper sway. It's like Mr. Norris. I be technically died back in like 2001. We were too afraid to tell you, and it's oh God. It's hey, maybe at peace. Poindexter's commenting. I'm wondering if it varies. It could be a method of signaling. Oh, well, I mean, aren't there? Okay, I'm pretty sure there are creatures. I think it's vipers, certain snakes, kind of see in the infrared. I believe. I can't guarantee that. The only being that I actually know kind of sees in the infrared, or at least uses technology, is the Predator or the Yaoja from the Predator franchise. Hence in Predator 2, when it seemed to acquire a taste for beef, all the folks that were trying to capture it, because that's obviously a good idea, they were wearing like the thermal suits. But ultimately, I think the Yaoja just tunes its sensors to just audio based, and yeah, good game for everyone else. No, they changed it to ultraviolet because they were using ultraviolet light to try to look for it. Yeah, that was a bad idea. I I think it's just activity. I don't know about conductivity. I mean, maybe. Well, I don't know how conductive are we. I think it would just be the total sum of our parts. Let me just conductivity. Let me actually. Oh, okay. Okay. I should probably actually learn more before I say that. I'm like, wait, do I even know what that actually is? We often think about it as just electronic transfer, but conductivity is a material's ability to transmit electricity or heat, represented by the symbol sigma. So, also the kind of the same for the Stefan Boltzmann constant. Uh, Sigma for electrical conductivity, it is the reciprocal of electrical resistance. 1 over rho, measured in Siemens per meter, S over M, or S over Cm. It relies on free charge carriers, electrons or ions, and is used to measure salinity or ionic content in water and identify material properties. Oh, reciprocal of electrical resistivity. Oh, electric resistivity. Oh, that's interesting. Ohms per meter. Oh, wow. Oh, they got the little chart here. Wow, quartz is apparently very resistive. Is is that why we would use it in watches? Rosaline, typical dry paper, 10 to the 10, typical glass, resist device, 3 times 10 to the 8. Resistivity of high quality distilled water, about 2 times 10 to the 7. Well, those are nice numbers. Oh, they crossed it out. Okay. Or maybe it's just the oh, no, it's the line from that one. Resistivity of a human brain cell at phone frequencies, 1 ohm per meter. Oh. So apparently within our given system, our brains resistivity at cell phone wait a second, why is it at cell phone frequencies? Resistivity of, let's see, about 0.2. Good iron, resistivity of gold. Oh, okay. So lower means more transfer because gold can warm up iron and the far end. Upper bound for the resistivity of high temperature superconductors. Oh. Okay. Ohms per meter. Okay. What happens to that magnitude? Oh no, it's like 2 times 10 to the minus 9 emus. Well, don't tell the Australians. Apologies, apologies. Sorry, couldn't help myself. Oh, that's interesting. Let's go back for a second. Let's take these dimensions. Let's double them because I'm just looking at this. I'm just in Planck units. I mean, you got length to the third, and then divide by time. That's the speed of light to the third power. Then you got mass, and then you got divide by charge. Oh, wait. No, this is tricksy. This is tricksy. No, I was wrong. Because time and current. Charge is time times current, or time current. I remember that because of the time warp. Do a time warp. I'm sorry. It's been listening to too much Jack Black recently. Um, okay, so that's 3. Okay, so we need 2 downstairs. All right, so we would do. Let me just another instance here. Let me just look at the dimensions, and we'll put them in here. So let's just do Planck units, Planck mass, Planck length, cubed, and then this all divided by Planck time, and then Planck charge squared. That was one of the initial things that really confused me because Thad was using charge, and a lot of times this Wolfram Alpha will just output usually in current because that's the recognized SI unit is the ampere or current, even though it's derived from charge. So take that as you would. Okay. Electric resistivity. Huh. This, I don't know about you guys, this number, at least that, okay, I gotta play. Hold on. I feel like we're gonna get back to our past definition here if I do this. Divide by h bar. Okay, it's going to be something like Planck mass because if we invert this, I'm just guessing here. It's going to be like 1 over 2.176 or something. Let's see. I might just be blowing hot smoke, but okay, yeah. And then when we multiply by Ampere's constant, then we. Okay, because it's got time current there. Okay, so when we multiply this whole jazz by Ampere's constant, it's going to give us a Planck mass. Constant. There we go. Why the heck do I even know any of this? Let's just say I may or may not have noticed this before just by playing with dimensions, and I'm like, what the heck is going on? There seem to be some very words here. Okay, hold on. So, long story short is This bookmark is from, I don't know, Planck Mass Digits Embedded in Charge. It was basically all of this stuff right here, kind of going through like what we just did, except I had no freaking idea why. So like I'm doing 1 over that number that we had there, except I think I'm using Thad's closed forms. Oh, look. Oh, we got those numbers. Oh. And then you multiply it by 10 to the -7. You're basically going to get. Oh, no. Wow. Oh, I put it in the wrong place. There we go. All right. And then if we add kilograms, it's going to tell us it's approximately the Planck mass. There we go. So it's, again, the dimensional calculator. Just getting a feel for these things. Yeah, that is interesting. What did I even do on the other one? We did that. So let me hold on. Let's divide it into H bar. It is interesting. If we just basically, do we multiply it the same way? Ampere is constant. Did I just divide and then divide again? What did I do the last time? Huh. Wait a second. I'm just let me move my bar. All right. Okay. Okay, so it's the inversion there. So then I would need to divide by it. Okay, it's inverse because, okay, well, we've got an inverse mass. Or actually, I just divided in. I should swap it. Because algebra is awesome. Yay! All right. Don't mind me. A lot in my mind just goes scatterbrained all over the place. So, all right. Let's go back. Let's go back. Okay. Ooh. All right. So I swear I'm catching up. Okay. Okay. So, okay. Yep. Yeah. Okay. Bats use sonar. Bats use echolocation. All right. Snakes hunt mice in the infrared. Oh, that makes it. And apparently, the surface tension of water seems to be remarkably strong. It. I don't know this, but it for some reason it kinds to resemble the fine structure constant. Let's hold on. Water. Properties more. It's okay. Okay. It's a little greater than 10 times the fine. It's about 10 times the fine structure constant. Okay, it's because it's 0.0. The fine structure constant would actually be 0.00729. This is 0.0728. So it's wedged in there with a relationship that I know is not exactly. So but apparently it's pretty good. 7.4 grams of force per meter. Okay. I guess that's how bugs and a lot of things can actually stand on the surface of water. Oh, well, wait a second. 50 millinewtons. Is that more or less? Champagne should be less. Okay, so it is less. All right, because I was going to say the bubbly. Yeah, I know. I think they usually fall into drinks if they're trying to stand on that. Uh, I have heard that, Tony, about, like, somebody, like, if they can't see and they're blind, they can kinda map it. I mean, that seems like a very, like, the story of humanity is to adapt and overcome, and I I've heard that. I've heard, like, I think there's been people that can still see that try to do that. It's I'm gonna fall down and, like, break my leg. It's I occasionally okay, sometimes it's like, I don't need to turn on a light. I can manage, and I'm stumbling around, and it takes far more time, and I'm like, I end up turning the light on anyway, so now it's like, let's just minimize the entropy here, just turn on the light real quick, do my thing, and then go do other things and live life, so alright. Hey, what's going on, crypto? What's shaking, my dude? Yeah, we're just doing some questions about different stuff and things going on. I learned a couple of things. I apparently oh God, where was that? I was on Codad on one of these things. Oh, we were looking at the mu naught, or basically the magnetic constant, and I had totally forgot that by definition it literally has alpha in it. So it's that damn fine structure constant popping up everywhere. Uh, but long story short was we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We got 12 significant digits for measurement. We got error about equivalent to the last two for a single sigma. So it's we got about 10 significant digits. It's kind of defined H bar because was it the first time I went to the monastery, I think I was unaware that they had updated SI, and that originally had the code out of 2018 numbers before the update, and H bar actually had 12 significant digits. The error was, I think, yeah, they should have it here. Hold on. It's 2018. Table of all values. All right. So, oh, did they change it? Because this is the new one, because they're cutting it off at the 10 digits, or was it 1, 2, 3, 4, 5, 6, 7, 8, 9? They're cutting off at 9. Oh, this is the 2018 adjustment. Okay, so they updated. All right, so we need to go back. Okay. Okay, so let's go to the 2014. There we go. All right. The Planck's constant. Yep. As we can see here, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I just can't count then. Because I could have sworn we had 12. Okay, so there's one more digit than before, but you gotta see it's like these last two digits. The error is twice the value of it. So that's kind of why we lopped it off. I think right over here because we got a little bit more precision. So that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9. Did they just give it more for each one? No, these are the same number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, never mind. I was just totally misremembering then. Ah, okay. So there was at least one additional digit, but you'd see the error there was fairly significant. That's why the more recent updates say, all right, we're lopping it off at 10. We got, at least with current precision, all the different stuff and things. So, did they have? I could have sworn. Yeah, 2018, an older archive of basic constants. Okay, because those are updated detail in the adjustment. Uh, let's see. Oh no, they did adjust it. 4, 5, 6, 7, 8, 9. Okay. Okay. Well, I guess that does make sense. I've been saying this wrong for a while. I just can't count. Uh, well, that makes sense. Well, if H bar is at 9 significant digits, we got 9 significant digits for the speed of light. All right then. Well, then of course it's we need to get you get the fine structure constant. It's literally defined off of elementary charge, and hold on, we get elementary charge. Let's just go to the modern definition. Charge. Okay, so we've got okay. This is now defined at 10 significant digits. So this is defined at 10 significant digits. We got 9 there, and then 1 is 10. And then we need the electric constant. And the electric constant, I think, is at 10. This may have been one. Like, sure. Oh, vacuum permittivity. Sorry. Vacuum. That's what they have it as. Yes, epsilon naught, the electric constant, vacuum permittivity. Is this based on alpha? Okay, no, it's based on the magnetic constant. So here we go. 3, 4, 5, 6, 7, 8, 9, 10, 11. We've got 11 digits, but again, we've got error for the last two. That means we've got high confidence in about 9, but it could go up a little bit there. That's the magnetic constant. So it's the inverse of the magnetic constant times the speed of light squared. And the magnetic constant was the first thing we were on, and that had, let's go back. So this has, okay, about the same. Actually, no, maybe a little bit more. Was it 4, 5, 6, 7, 8, 9, 10, 11, 12? I got 12 significant digits. Also got error in the last two. So lopping things off around 10 significant digits kind of, that's interesting. Some of these constants they'll define, other of those they'll kind of just lop off. So we're trying to make things a little bit easier. All right. All right. I was gonna say we could either do something tomorrow, if you need crypto to talk, because we're having our monastery meeting usually at 3 p.m. Eastern time, so like Boston East Coast time. So we have that then. So either before or after that, we could probably do something. If it's a short thing, maybe for a few minutes after this, I'm almost done. Let's see. Rick is commenting. Quartz is a piezoelectric crystal that vibrates in the presence of electricity. A digital watch has tiny quartz tuning fork as the time reference. Okay, because apparently, just those old watches, it's like you just move your wrist and say, "Oh, there's some vibration and stuff," and it seems to work. Every once in a while, I just wind it. It's I don't know. It's how do those Swiss watchmakers make such crazy things? Occasionally, I'll watch a show on it, and it's just my inner little kid comes out. I'm like, look at all the gears and the stuff and the things. Let's see. Oh, I think. Listen, most of these things that I've learned from other people. It's whether it's Thad or like Rick. Rick is AFK right now, but I've learned a bunch of so much from Rick. And even just folks here in the chat, like Tony points out things yourself. Uh, that's the thing. You never know where a good idea comes from, or even it just. I think Sam Harris said this best. It's like, all right, if you hold a particular stance on something based upon your knowledge of what's going on, okay, that's cool. But if you get new information, and that's going to update your priors, and especially if it's significant information that maybe you're just wrong. That seems like it's important information, and you would adapt your opinion unless there are underlying reasons why you hold that opinion. My thing is just be honest. It's like, okay, I prefer this thing. Why? Because I do. If you admit it's like, listen, I'm not saying it's rational. I just prefer this thing. It's like, okay, that personal opinion. Personal opinion is a thing. Uh, uh all right. Hey, I'm happy. I can take all the help I could get. Uh, as long as it's within certain parameters and everything. As long as I don't need to sign away certain things. Okay, again, okay, that is a private call. All right, we won't get into that. Uh, okay, well, hey, okay. Johnny Water is literally. It seems like magic. It's one of those things that like we're mostly made of it. I tend to personally am of the opinion we tend to go the path of least resistance. Um, just a little meme, but to be fair, water is. Water is not an element. It's a chemical compound. At least according to our thought process on this. I say this because uh, I actually have God, I feel like there's a was it Shiloh and Anastasia from Demystify Psi? They had another episode of Paradigm Drift like a week or so ago. Um, I got pulled for like a fifth time from the hat, which I guess is statistically possible. And then again, I also like applied every single time. Um, but I was presenting something, and there's this crazy calculation where at first, I'm not gonna lie, I totally forgot that water wasn't an element just because it's always there. And you're like, oh, we always see this. So you think, carbon, soot. I see that stuff all the time. It's a chemical compound. However, water has some fantastical prop. And I think I asked this. I asked this to at least chat. So we model it as incompressible. Technically, you can kind of do it under extreme circumstances. I just, at least to my knowledge, because I went back and forth through this. But the interesting thing is, it seems the number one determining factor of at least the density of water, and water is very often combined with other things, whether it's salt or just different stuff and things around. It's that the density of water is primarily a factor of its temperature, which it reaches its maximum density not below freezing, because once water starts to take on an ice form, its density increases. So it's kind of like when you're a little kid. It's if you've got a full sippy cup of something or just a full glass or whatever, if you're gonna put it in the freezer, because I want it to get cold, make sure you remember it, because if it freezes, it's gonna be end up overflowing from the glass there. So that's why if yeah, it's one of those things you learn as a kid, and a lot of times you don't think much of it. But the maximum density of water is like just under 4 degrees Celsius. It's really dang close to about 1 gram per cubic centimeter, which is a weird thing. It also happens to be what the Newtonian gravitational constant was originally based off of in units. I learned that from Rick. Apparently, it was when Newton came up with the gravitational constant. He's like, all right, you got your mass one, you got your mass two, you divide it by your r squared, or no, excuse mass one times mass two, divide by your r squared, and basically you're going to end up getting out your gravitational constant or proportionality and everything. Okay. Cavendish actually like added units, so he just used the reference density of water. Why? Well, originally the original kilogram, which is called the gray, was based on the cubic value of 10 deciliters of water, slightly above the freezing point. I mean, what do you want to say? It seemed to be really well. And it's like, all right, now you have a historical reference. And again, I'm not saying this is the preferred basis of the universe. I mean, that would be kind of rad if it was. It's almost like there's an Easter egg built in, but basically it linked the kilogram to the meter. Because if 1 gram, you remember it's, yeah, when we used to count, when you do it's like, all right, you got your little block. I'm not going to draw all the little blocks just because it's a bit too hard, but it's like, all right, you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You get 10. Now you do your 10 rows. I didn't count for that. And then you eventually build it up into a third dimension. So basically, long story short is you can have a cubic centimeter of water at 1 gram. You lay out 10 of those, you get 10 grams. All right. You lay it out in the other direction. You tile all those things. You take that first row, you have 10 of them. Now you have 100 grams. Okay. And then if you go up another 10 rows in the next dimension, you have 1,000 grams, aka 1 kilogram within 10 centimeters, cubic centimeters of water. I'm like, wait, hold on, wait. You're saying those charts that we saw in like elementary school and stuff, like you could have actually done a physical correspondence to that? I feel like they may have had that. I think I just ignored it. We'll call it a happy coincidence. Now, again, I don't know if I'm just saying if I do the naive thing, sometimes very interesting things seem to pop up. And again, maybe it's just a coincidence, but I like to imagine such things. But listen, I'm going to show you the crazy thing, and I literally needed to check myself because I literally, in my mind, it was listed as an element because it was so common, especially when I did this calculation. Let's take the sum mass all elements. Okay. I just know this because I've typed in words before and I'm new. You could sum the periodic table of elements by what we standard put in there. And again, not all the isotopes, but one of each element in the standard common form of which we know it. And to be fair, I got chat to go sum up the particle data group stuff or whatever it had there. Long story short, it gave me this number about plus or minus 1 because there is some uncertainty because element 118, oganesson, we made maybe a dozen atoms ever. So there's some uncertainty there. But I'm like, all right, if water had some fundamental thing, maybe I would find like, take the sum total tessellations of mass, assuming that this is the end of the line. If some folks theorize that you could go up to element 137 because of fine structure constant. Coincidentally, the periodic table seems to be neatly complete. Maybe we can get higher, I don't know. But I figured, well, if water, and again, I totally forgot it wasn't an element. I'm like, well, if I divided it into this, maybe I'll get something like the fine structure constant. So let's just divide by the water mass. Okay, 1 molecule of water does not yield the fine structure constant. So I'm like, okay, maybe a hexagon of water. We'll do 6. So 6 times the mass of water. Okay, that didn't work. So I'm like, maybe 7. That's breaking scale symmetry. So what are the chances? And 137. That's odd. My first response is it's rounding. Okay, let's just go to this. Let's just take the mass of water. Let's just take the physical number. Okay, I'm just gonna take the number in kilograms. All right, steal that. It's the mass of 1 molecule of water in kilograms. Let's take all the elements. Take it in kilograms. Let's divide it by 7 times that number there. And the terrifying thing is, apparently within the uncertainty of the periodic table of elements, it's not just 137, it holds for almost 2 significant digits. Because the next 2 digits of the fine structure constant are 3 instead of this 4, 3, 5, 9. No, 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 yes. It's 3, 5, 9, and the low end of the periodic table gives just below the fine structure constant. The high end seems to be about a 5, so again, this is just straight up numerology. I was looking for something. I hypothesized maybe there's a relationship. Now, it wasn't 1, it happened to be 7. Now, why is it there? I don't really have a good reason other than just numerology and saying, "Oh, I'm looking for this. Oh, this helps support my cause." Now, if anybody has any ideas and reasons why, that's one of the reasons why I wanted to present it at the last Paradigm Drip taping they had. Because number one, at least 2 of the people there, Shiloh and Michael Hughes, they both worked on water for like their PhDs and everything. So I'm like, what's going on here? Is there any? It was also right up their alley. So I feel like that made them maybe a little overly kind to me, and it just I don't know, just consistency is all. Charlie, what's happening, my dude? Well, we're just finishing up some numerology there. All right. So, well, that's the other thing. It's like growing up. It's like as far as neutrality, it wasn't water like 7. It's like was it heavy bases are 0, heavy acids are like 14. I may have inverted that, but I think it's that way. But water was always seemingly at the center or right about the center. So it seems to be one of those convenient things. Now again, I it can be a very woo-woo thing. So that's why I have to caution the heck out of it, because it's like, aside from me wanting it to be this, and maybe an anthropocentric argument, I don't really have any other good reasons. I mean, maybe just I mean, it'd be awesome if it was the case, because then we could just meme Bruce Lee and be like water. So yeah, it's I Rick has showed me some things like about a year or two initially at the monastery. He's using the reference density of water. And I was very dismissive of it, and the more and more I work on this, I'm like also realizing, well, we need a justification to give the kilogram significance and everything before we divide the it into the Planck mass for that's hyperbolic partition equation. But that's a whole other story. It's you, yeah, Charlie, dude. The stickiness, it's the oscillatory stuff through water tends to go faster than you would normally model your quote unquote particle like collisions and stuff, because apparently because of those 2 hydrogen atoms there and the way it seems to flip, it seems to communicate at a faster rate than one would typically suspect. And then there was also a Wolfram Institute project where something you would normally think that they were using like water to compute or liquid computing. And you would normally think, okay, if you're going to surround something, it's going to be like a dodecahedron. You get surrounded by 12 things. It was a very weird thing with water where apparently it was like 12 point something, because through their simulations, it's like water occasionally seems to start to sneak in a little bit more. And you're like, Donnie, that's weird. But yeah, no, it is a crazy thing. There's so much stuff that we don't know. Bacteria, I would ask Stephen Wolfram that, because as far as I know, we're still finding bacteria and stuff in the Arctic or other frozen places, and occasionally it's like we warm it back up. Oh, look, it seems to come back alive now. Maybe you should be wary. I don't know. Maybe I've just watched too many Godzilla movies and realizing that occasionally thawing organisms that were frozen in ice can lead to to not so great things. But then again, who am I to say? It's not my call. Welcome, Tony. We're just wrapping up. We're speculating over, is it just all water, bro? Which raises a whole bunch of questions, but again, aside from wanting it to be true, for a whole bunch of reasons, I feel at least the Bruce Lee memes of "Be Like Water" would be powerful, and I don't know, maybe shed a little bit of wisdom onto some folks. But Yeah, and Tony, even was it, I'd criticized, my friend Casey, a gangster mathematician over this, but he said they basically were using water to simulate a black hole. And apparently, it was absorbing all the sound. I'm like, well, that's not a black hole, or at least a black hole in the physics sense of creating like a super dense thing. But in practice, from a mathematical basis, it's okay. I think he was right. So, uh, oh yeah, no, that's what I read it as. Oh, yeah, I'm not a biologist. I don't know about that stuff. It's well, it. I mean, we are mostly water, and apparently, as we look back further and further into the universe, we occasionally seem to be surprised by large amounts of H2O and maybe ice form and everything. You're like, wait a second, isn't this, according to some of our models, seems a little early for there to be water there? What's going on now? Again, I could speculate, but I can't say that that is the case. Uh, oh, geez, the pure condensate. Yeah. They're a very interesting thing, but then again, you'll see it's like you have a certain like frequency, and then all of a sudden it's like they'll oscillate water, and like water apparently seems to, or maybe drips of oil or something. You're literally seeing it do things that is believed to resemble particles doing stuff and things. And it's maybe we'll do that for another day. But yeah, hey, who knows? It's I didn't create all this stuff and things. I don't know who, what, when, where, or why. I'm just some meatbag conjecturing with all you, and right, we'll see where it goes. But okay, I've been blathering for over an hour, but okay, maybe we'll do a few more of these. These are kind of fun as long as I can get prompting and go in all different directions, which seems to keep me in my ADD mode and just jump from one thing to another. So maybe this is more fitting of doing live streams, but that's all I got for right now. So hey, peace out, everybody. Take care of yourselves. It's a wacky and wild world out there, but you do what you got to do so you can do what you want to do. Why? Because we can. And do whatever you want with this content. I ain't your dad, at least of my knowledge. So have a good Friday, everybody, and peace out.